This lesson is about the disorders that arise from extra chromosomes or missing chromosomes. And we're talking about the entire chromosome is added, trisomy, having 3 copies, or removed, monosomy, 1 copy. You can imagine that the body does not tolerate excess chromosomes very well, nor does it tolerate missing ones. We learned about Angelman and Prader-Willi, where in those cases there was an extra deletion in addition to methylation. But those genes were turned off by methylation, one section by dad, one section by mom. Having that methylation fail, having one extra gene causes real problems. Prader-Willi and Angelman are from the deletion of the chromosome plus the methylation, loss of the gene. But my point is, on that spot on chromosome 15, having 2 copies of the gene be active doesn't work. Gene on a chromosome. We're talking about adding an entire chromosome. Okay, so to start us off, let's just cover some vocabulary. A cell or an organism is said to be euploid or exhibit euploidy when there is a multiple of the normal amount of chromosomes. That is, in humans, multiple of 23 chromosomes. That is, we can have haploid or haploidy, where we have a complement of 23 chromosomes, that's 1N. Diploid, where we have 2 complements, it's 46. If we have 3 complete complements, it's triploid, 69. And if we have 4 complements, it's tetraploidy, 92 chromosomes. So euploidy doesn't mean the right number. Euploidy means any multiple of the correct amount. We have chromosome 1 through 22 plus a sex chromosome for a total of 23 in our gametes, and our adult cells, the somatic cells, have 2 copies of each chromosome. So the diploid is us normally. This is all somatic cells, not gametes. Haploid cells are our gametes. Now, our body does not like haploid cells, and our immune system will attack it if exposed. But both haploids and diploids occur normally in us, so they're good. Tetraploid, never will take. It'll be fetal demise, fetal loss, will never be brought to term. Triploid fetuses can be brought to term, are usually stillbirths, and if they are actually birthed, they die day 1. In fact, having triploid is more likely to end up being a molar pregnancy rather than a real pregnancy. We'll learn more about that in reproduction. The point is that adding a full complement, body can't handle that. So we call an organism aneuploid, exhibiting aneuploidy, when there's not a multiple of 23. And you'd think, if we were even talking about adding an entire set of chromosomes, there'd be a lot to learn here. No, there's not, because it follows these rules. Any autosomal monosomy, that is, if there's only 1 copy of an autosomal chromosome, non-viable, dies. The second is the organism can only tolerate 1 change, that is, 1 addition or 1 deletion of a chromosome. There's more than that, dead. Which means that aneuploid will always be either 45 or 47. Any other combination is dead. 45 means lost a chromosome, 47 means gained one. All autosomal monosomies not tolerated, organism dies. There are only 3 trisomies, that's convenient, 3 tri, that can come to term. And that's going to be 21, 18, and 13. 18 and 13 definitely dead within the first year. Most die within the first month. 13 in the first week. So there aren't a whole lot of disorders that you're going to need to be able to identify. If the organism is birthed, you know that it's either euploid, and being birthed, not a gamete, it'll have 46 chromosomes. Or it'll be an aneuploid, which can only be 45 monosomy of one gene, or 47 extra copy, usually trisomy, but we have to play with sex chromosomes and these 3 chromosomes, letting us have to deal with only 5 disorders. This happens because of non-disjunction. There are other ways that this can happen. 2 sperm fertilizing 1 egg simultaneously, get you triploid. But what we're going to study right now is non-disjunction. Non-disjunction refers to the failure of chromosomes to separate. The way meiosis is supposed to go is meiosis 1 will have homologous chromosomes, each with 2 chromatids, line up next to each other and then separate. Non-disjunction of meiosis 1 ends up with 2 cells, 1 cell without any of that chromosome, 0 chromatids, and another cell with 2 chromosomes, 4 chromatids. When meiosis 2 happens, that cell that didn't have the chromosome at all can't have any, and the cell that had too many ends up with double the number of chromosomes. If that non-disjunction pairs with a haploid gamete, normal, regular, what you end up with as the possibilities are 2 trisomies, 1 monosomy. The other thing we have that can happen is non-disjunction in meiosis 2. So during the first meiotic division, the homologous chromosomes line up and are separated from each other. Each still 1 chromosome, 2 chromatids. And then non-disjunction of meiosis 2 usually is going to occur in only one of the 2 cells that are dividing, because these 2 cells are independent of each other. So non-disjunction of meiosis 2 creates 1 cell with 2 chromosomes, 1 cell without, and the normal meiosis 2 gives us 2 cells, each with 1 chromosome. If we pair those with the haploid gamete, normal, what we end up with is actually 2 potential normals, disomic, normal, 1 trisomy, 1 monosomy. Point is, if you're going to change the number of chromosomes, non-disjunction is the way to do it. So now we're actually going to walk through the disorders. There's a lot of details to know in each one, and you do need to know them because they are rare. They also are very descriptive, and they have a lot of elements that aren't going to appear in other disorders. So you should be able to identify which disorder it is, and then what you need to then have is, what are the associations that go with it? Let's do the autosomal trisomies first. Down's syndrome has a D to remind you that it's the drinking age. And the drinking age is 21, so it is trisomy 21. Down syndrome is the only one of the autosomal trisomies that can live into adulthood. So they're going to be the most common. The other ones die. The most common chromosomal disorder, and also the most common cause of genetic intellectual disability, mental retardation. These patients have a variable expression of the mental retardation. Some have completely are incapable of taking care of themselves, and some can actually have a job and live independently. There is no way to assess by the genes how bad their intellectual disability is going to be. You'll be able to spot them by key features of having the syndromic face, which is flattened, a single palmar crease, and what you need to know about once you've diagnosed Down syndrome is what are the associated diseases or problems that they might develop. Down syndrome is associated with congenital heart defects, endocardial cushion, which might lead to a ventricular septal defect. This is a congenital heart defect. Also, Hirschsprung's, which you'll learn about in GI, as well as duodenal atresia. The thing that we now know, which actually helps us understand Alzheimer's better, is that on chromosome 21 is the APP gene, amyloid protein precursor. Because there's an extra chromosome, more of this gene gets transcribed, more APP protein gets made, and we see that on top of their intellectual disability, there is early Alzheimer's dementia. So if they live into their 40s, on top of their intellectual disability, they end up starting to have progressive dementia. This disorder gets stressed a lot for prenatal screening. There's a couple of ways we can do this, which we'll talk about in reproduction and then in OBGYN in the clinical stuff. The keywords I want you to look for, without going into great detail, is